Hello everyone, welcome to my YouTube channel. Let's solve the fifth problem. Let's read the problem statement. So the problem statement is we have to find the minimum in a rotated sorted array. So the array is given which is rotated as well as sorted, and you have to find the minimum element that is present in the array. So the minimum element that is present in the array is 1, so you have to return the minimum element, right? I hope you understood the problem statement. Now what can be the brute force approach? Brute force approach is, as we have to search, so we can apply linear search here. So we can traverse the element array entirely, and then we can add one conditional check to check whether the given element is minimum or not, right? So what is the time complexity of linear search? We have to traverse the array, so worst case time complexity is order of n, space complexity is order of 1, right? So this is a brute force approach. Now can there be an optimized approach? Yes, because as it is given in the question that it is sorted, so whenever there is a question that tells us ki the array is sorted, then we can apply binary search, right? In this question we can apply binary search. But let's now compare how this question is different from the standard binary search question. So in standard binary search, the value of k that we wanted to search is given, right? The k is given to us, right? It is given. But here we have to find the minimum element, right? So the element that we are searching is not given, right? So we have to apply condition where we will check the minimum element, right? We will do some check that we can find the minimum element, right? So this is how it is different. This problem is different from the standard binary search approach. Another way it is different, or it is different compared to standard binary search approach, is that in the standard binary search approach, right, we don't know, we are not sure whether the k is present in the binary search or not. We are searching. So the condition that checks while low is less than equal to high, right? This condition we apply in the standard binary search. Low is less than equal to high. But here we are, in this question we are for sure that there will be minimum element present in the array, right? We are very sure that there will be, even if there is one element, then that one element will be the minimum element. So we are confirmed that the minimum element will be present in this rotated sorted array, right? So instead of writing this condition, what for this question we can apply while low is less than high. We will not check for equal to, because we are confirmed or we are sure that there will be minimum element present. So these are the two ways how this question is different than the standard binary search approach, right? So let me do some dry run for a sample example to get it more clear. Let's say the array element is 40, 50, 60, 70, 80, 10, 20, 30. So this is the array element, and we wanted to, let me do indexing as well. So for binary search we will take two pointer, one pointer is low, other pointer is high, right? Let me also draw the table that we are doing till now: low, high, mid, and action that we need to take, right? So low is 0, 0, high is 7, middle element is low plus high by 2, which is nothing but 3. Now this 3 is m1, right? Now we want to find middle element, right? So I can compare this mid one to either this low pointer or high pointer. So let me compare middle element with the high pointer, right? Because this is a sorted array. So if array of mid, here array of mid or m1 or mid that we are saying is 70 and array of high is 30, that means array of mid is greater than array of high, right? Let me write it mid only. so that you don't have any difference of point. So here array of mid 70 is greater than array of high. If this will be the condition, that what action we can take, then we are sure that the minimum element will not be on the left side, it will always be on the right side. Why? How we are confident? Because if the middle element, as the array is sorted, right, so we can confirm that if the high is minimum compared to array of mid, that means array of mid is greater compared to array of high, then what action we can take? We have to move towards right, because we are sure that the minimum element will be on the right side, not on the left side. So if we'll move towards right, which pointer I need to update? I need to update low pointer. Low will be mid plus 1. So mid is 3, 3 plus 1 4, so updated low pointer value will be 4. Let me extend this, right, and high is 7. So 4 plus 7 by 2, which is 5. Now 5 is the middle element. Now 5 is the middle element, right? Let me write 5 is middle, low is updated to 4, right? Now again we will compare array of mid with array of high. Array of mid is 10. Now array of mid is less than array of high. So what condition is happening here? If array of mid is less than array of high or equal to, you can apply here condition, then in that case we are sure that the array element will be not present on the right side, right? Because the high is increasing and the middle element is less, right? So we are confident that the minimum element will be not on the left side. But we are not sure about what if there might be possibility that what if the middle element is the minimum element, right? So that's why what we will update our high boundary, right? What we have to do, what we have to go, what action we have to take? We have to move towards left, because we are for sure that the minimum element will not be on the right side. But we will update our high pointer in the way that we will not update high to mid minus 1. Why we will not do that? Because there might be possibility that the middle element is the minimum element, and in this example it is showing that the minimum element is the middle element, right? So that's why we will not use this condition. We will use high is equal to mid, because there might be possibility that the middle element is the minimum element, right? So if we do mid minus 1, then our condition will be false, right? Because I told you in the starting only, I told how this problem is different than the standard binary search problem. Because in the standard binary search problem, k value is given. So if the k value is given, then we can compare the array element with the k, right? So equality condition we can compare. But here in this question, we have to find the minimum element, we have to find that k. So that's why we have done here high is equal to mid, right? Let me complete the dry run as well. So now what will be the low? Low is 4. Let me write here, low is 4, high is mid, which is high is updated, high is 5. Now 4 plus 5 by 2 is equal to 4, right? Now this is the middle element. Now this is again middle element. This is high, this is low, this is mid, this is high. Now again we will compare low with, our middle element with high, right? Our middle element with high. So here mid element is greater than high element, right? So this condition is satisfied. Then we will move towards right side, right? So we will move towards right side. So here what is happening? here if array of mid is greater than array of high, so in this case we will move towards right, so we will move towards right. So which pointer we have to update? We have to update low pointer. Low will be mid plus 1. Mid is 4 plus 1 5, so updated low value is 5, high is 5. Now at this point, if low is equal to high, then we will end our loop for this problem, right? Why we are ending our loop? Because I have already explained how this problem is different than the standard binary search, right? Because in the standard binary search we are not sure whether the k is present or not, so that's why we are doing while low is less than equal to high. But in this question we are confirmed that if the array is given, then there always exists the minimum element in the array. So that's why we are not going to condition while low is less than equal to high, we are only going to the condition while low is less than high, because we are sure about that the array will contain minimum element. So that's why we will end our loop here. Okay, I hope you understood the dry run, right? Let me quickly write the code for binary search. Okay, so let me write the code. Let's say the function is we have to find minimum. We are taking an array, integer n, right? We will first initialize low to 0, high to n minus 1, while low is less than high. I told you why. We'll write different because we know that it is how it is different. I already explained. Right, now we'll calculate middle element. So to calculate middle element, we know that low plus high minus low by 2. Right, now what we'll do, we will check the condition, right? What we are comparing? We are comparing array of mid if greater than array of high. If this is the case, then what action we need to take? We have to move right side, right? So if we will move right side, then which pointer I have to update? I have to update low is equal to mid plus 1. Low is equal to mid plus 1. Else, in else case, if, let me write the condition also, array of mid is less than equal to array of high. In this case we have to move left side, right? But we will move in a way that high should be mid and not mid minus 1. I already told, right? This is the difference when we compare with the standard binary search problem, right? In the standard binary search it is given mid minus 1, but in this problem we don't know the mid element, so we will only update our high pointer to the mid, because there might be the possibility that the middle element is the minimum element. Mid pointer might be the minimum element, right? I have already told in the dry run why, right? So, and then we will end our while loop, and what we will return? We will return the minimum element. So minimum element will be at the index of high pointer, so we will return array of high. So this will return our minimum element, right? So this is the code. For applying binary search to find the binary search in the minimum, to find binary search in rotated sorted array. Now let me quickly write the time complexity and space complexity. As we are applying binary search, so what is time complexity of binary search? It is order of log n, and space complexity is order of 1, right? So this is the optimized approach to solve this problem. We have reduced our time complexity from order of n to order of log n. So thank you for listening.